With that, let me introduce Mr. Baym.
Thanks, Evelyn, very much. I'd like to see you all here. This will take a moment to get going. How many of you have cell phones? Okay, you'll find out where they come from by the end of the talk. It's all related. Let me get this thing going. Yeah. Very good. This year, 2025, is the 100th, officially the 100th anniversary of quantum mechanics. And what I want to talk about is where did this thing called quantum mechanics come from? What is it? What is it good for as well? Let me see if this thing works. Ooh. Okay. 1925 is a little bit arbitrary. The story really began in the late 19th century here. But what was going on from the mid 19th century until mid 20s, people were just struggling, grasping at all these new ideas, trying to make sense of them, and they really many false starts and many good ideas that were not understood at the time, and so everything began to fall together in 1925. So what I want to do is tell you a little bit what quantum mechanics is, and then how did it all begin? Well, quantum mechanics is the framework that physicists use to describe the microscopic world. We're all used to the physics that describes the classical world, Newton's laws of how the planets go round, and you step on the brake, it stops your car, and all this stuff is sort of the elementary, what we call slide and glide physics that you learn in high school. Quantum mechanics is asking questions of what goes on in the microscopic world. One of the characteristics of the microscopic world is when you try to do a measurement, you have to use the tools of the microscopic world, and the measurement interferes with what you're trying to with the system you're trying to measure. That's a peculiar feature. Another peculiar feature is that particles are sometimes described as waves. Waves are sometimes described as particles, and there's a big confusion here of things, particles and waves. I hope I can explain what's going on. What's interesting about the waves is they can interfere with themselves, just like if you drop two pebbles in a pond, they will make a pattern like this one over here. You see waves going up, but where the waves intersect, they make different patterns here. Another important feature of quantum mechanics is that when you do a measurement, you don't get a definite answer. You can start with the same system many different times, and you get a range of different answers. And what quantum mechanics tells you is what's the probability, what's the chance of getting a given answer here. It's sort of, as Einstein put it, God rolls dice. I mean, Einstein said God doesn't roll dice, but it turns out he rolls dice. Okay. The other feature of quantum mechanics is that it's a tremendously good theory. I mean, everything it tried to describe works perfectly. Yet there's still questions we physicists do not understand about what goes on in the process of measuring things, and how the measurer, the observer, interacts with that. Okay. Now let me back up the history of this, where it all came from. What I want to focus on in this talk is how we got from these 19th century mysteries to the smartphones essentially 1 century later. And I think the important century has been one from the late 1890 to 1990, really. And for this, no. Okay. Well, the first question, people were understood when you forged hot metal, you heated it, and the metal was glowed, and the metal was red. And the hotter the metal became, the more. If you look down here, is you can see sort of how the color is correlated with the temperature in Celsius or Fahrenheit, depending upon use. We're also familiar with an ordinary electric burner on a stove, which is roughly around 1500 degrees Fahrenheit, glows red. As things become hotter, they get more and more blue. As I think you go from the left to the right along here. And the question is, how do people get from worrying about where did the colors come from to our smartphones? Just 1 century. It was really quite a spectacular development here. Now, and these clickers are also a result of quantum mechanics. Okay. The first question: how to understand the colors? Back in the 1890s, this was a serious problem. You heated things; they got more yellow, more blue, and they also. Oh, it's terrible. Ah, they're good. And they got brighter here. And what was funny is the question is, why was there sort of there were different colors available? If you had to analyze the frequencies of light carefully, you saw there's a maximum here, and the hotter the system, the bluer the things became. Oh, it's a complete mystery. The physicist Max Planck was extremely famous. In 1900, he tried a very simple trick. He said, light's coming out of these things. Suppose it's not coming out smoothly, but suppose it's coming out in little droplets, like raindrops falling. And what he found is, miraculously, he could explain the colors. He had no idea what was going on at all. I mean, what he said was that the energy of light coming out was proportional to the frequency of the light that's being emitted, how fast the light oscillates, times a number which is called h, which is known as Planck's constant, appropriately. No idea where this came from whatsoever, but it was the right answer. It was a big clue. Okay, I just want to show you that's Planck down there, but that's not. There he looks like a physicist doing work. Sorry. That's his formal picture over here. His great man picture. Okay. There's another effect called the photo effect. This was discovered by Heinrich Hertz in the late 1887. He's the guy who invents megahertz, MHz. It's after him. What he did, this is his original apparatus over here, but he shined light on this. He shined ultraviolet light on a metal plate, and lo and behold, electrons got knocked out. What he actually saw was between the two ends over here, he shined light on one end, out came electrons which floated across. It made a spark. Here. This could not be explained by any physics that people knew in the 19th century. Here. So this is basically the picture here. The light falls on its plate, and electrons get knocked out. This work was also a complete mystery. But then along comes Einstein, 1905. 1905 was a very special year for Einstein. It's called the Anno Mirabilis, the Year of Miracles, where he did 3 incredible pieces of work. I mean, he explained the photo effect. He wrote down the theory of special relativity, how very fast objects move. Space-time is not quite what we think about. That's a different lecture, though. And the theory of Brownian motion. If you look through at a liquid very detail, you see particles jiggling around. What that jiggling is all about. That was sort of really one of the crucial things in understanding solid state physics, matter physics together. And then in 1915, he wrote down the general theory of relativity. It was spectacular. But what Einstein said was very simple. He said, yeah, Planck was right. Light does come in little bundles. These little bundles are known in this building as photons. But that term didn't come into the late 20s. And those are little bundles of light. And light does come in fact. All this stuff over here is coming in little bundles. So Einstein was right. And it turned out that Planck had really found something very fundamental without understanding it here. And Einstein came 1921. He was given, I would say given the Nobel Prize, but 1921 they figured they didn't have anybody qualified for the Nobel Prize, so they gave him the 21 Nobel Prize a year later. So he got it in 22. He got it for the photo effect. What was peculiar for the physicists in the audience is that understanding the photo effect does not require the existence of photons. So that was an interesting story. Okay. People thought this idea was crazy. I mean, here's Planck. He wrote, Planck in 1909 he wrote down this quote. This Planck was 1900. He said light comes in little bundles. They say, well, no, rejection of Maxwell's electromagnetic waves used to be a step which is not yet necessary. Planck didn't understand what was going on. Other comments, but Niels Bohr, who's the quote father of quantum mechanics, he wrote 1925. This is 20 years after the photo paper. Even if Einstein sends me a cable, then cables back in those days, sends me a cable that an irrevocable proof of the physical existence of light quanta, these photons, has now been found, the message cannot reach me because that's being transmitted by electromagnetic waves. not little bundles, they're just going out. He also was very interesting. Bohr, who we'll come to later, spent his whole life trying to understand so we really need photons. It was okay, I want to switch gears. This was all about light and understanding what colors of hot things. Earth Rutherford, who was from New Zealand but spent his productive career in Cambridge, England, is effectively the father of nuclear physics. He plays now a very, very important role in the story. He got the Nobel Prize in Chemistry in 1908, worrying about radioactivity. But the important physics things he contributed in 1911, what he did was he took the nucleus of a helium atom, which is called, physicists call it alpha particle, and he bombarded atoms with, I'll show you better pictures, he bombarded gold with it, and found sometimes they would bounce back, sometimes they would bounce over the angles. And what he learned from this is that the nucleus, the atomic nucleus of the atom around, has a lot of electrons going around, but there's a very tiny nucleus inside. I'll show you more pictures of this and why. Then in 1918, he discovered one of the building blocks of the nucleus, which was the proton. So we'll see more of this as well, which is the little building block of the nucleus that has a positive charge. He was very opinionated. all physics, all science out of the physics was stamp collecting. Oops. Okay. So let's think about atoms for a moment. Rutherford's thesis advisor in Cambridge was J.J. Thomson. J.J. Thomson had a theory of the atom that was just a big ball, what's called the plum pudding model. It's a big ball of positive charge with the little electrons inside, so the whole thing was neutral as a whole. Rutherford's experiment was to shoot particles in, and if they went past the nucleus, they would just go in straight lines, but occasionally they would just bounce back at big angles. So he saw this very strange thing that most of the time nothing happened, and some of the time there'd be very big scatterings. Whereas it's the same thing with electrons going through Thomson's plum pudding, or the particles going through, they would just sort of wiggle a little small encounters. But he really, from this experiment, saw that the nucleus had to be a tiny thing. How tiny? The nucleus is about 10 billionths. The atom is about 10 billionths of a centimeter, and the nucleus is about 1,000th the size of that here. It was very important. And so here's a picture of the nucleus, the 10 millionth the size of an atom here. It's composed of two kinds of particles, neutrons, which are neutral, and protons, the blue things, which are a positive electric charge. He discovered proton, his thesis advisor discovered the electron, and his student discovered the neutron. It's quite amazing. Here they are. This is J.J. Thomson discovered the electron, Rutherford the discovery of the proton, and Chadwick in 1932 who discovered the neutron. It was a pretty close cooperation then. It was quite wonderful. there's another mystery, which is that if you're probably all familiar with sodium vapor lamps. They cast this horrible yellow glow over things. Different atoms, if you have a gas of atoms and you heat it, they glow very specific colors. I mean, so for example, hydrogen would glow with this reddish thing in a blue line, and helium, different colors, mercury, and so on. Uranium is much more complicated. Of course, these colors are used by astrophysicists to study stars and just figure out what they're made of here. But why this was happening, again, another complete mystery that had nothing to do with the original question of what metals glow. This was a whole different question. It's individual atoms glowing here. And along came Niels Bohr. Niels Bohr is Danish, born in 85, lived to 62. We actually was a postdoc at Copenhagen at 60 to 62. We actually met him. In 1913, he wrote down a theory of the atom called the Bohr atom. And then in 20, he led the development of the theory of the quantum mechanics. This shirt I'm wearing here is actually, in 2013, there was a conference in Copenhagen to celebrate 100th anniversary. So this is a picture of a Bohr atom over here. And it says down here somewhere, 100 years. And the back says the Niels Bohr Institute. When Bohr died, he had his own institute, the Institute of Theoretical Physics in Copenhagen, which still looks like this. And then after he died in 62, it was renamed the Bohr Institute. This is the famous Auditorium A in the Institute, because there was a conference in 1930. Yeah, exactly. Somebody superimposed a picture of a Macintosh computer. But actually, this is very funny because there's a little toy trumpet over here. That was real. It's sitting in front of Heisenberg. Anyhow, Bohr died in 1913. He was 14 and 27 years old. 1911, so 25 years old. He wanted to go to abroad from Denmark. So he wanted to go to England to study. And so he wrote a grant application. This is his grant application in its entirety. And here translated. Copenhagen, 20th June 1911. Undersigned permits himself to request a travel stipend of 2,500 kroner, which is about $400 in today's money. No. Yeah. For a one-year study stay at foreign universities. Sincerely, Niels Bohr, Doctor of Philosophy. He said this is the Carlsberg Foundation Director. He got the money. Try that now. If you got the money, try it now. Okay. So Bohr went to Manchester, where Rutherford had his laboratory. Manchester, went later to Cambridge. There he from 1907 to 1919 was there, and there he developed this model of the atom. They were always good friends. This is Niels Bohr and his wife, Rutherford and his wife. Here. And he came up with a very simple theory of the atom, which is illustrated here, which is that electrons go around the nucleus. He knew about the nucleus because Rutherford had already discovered it, and go around just like planets go around the sun. But the only difference is that the allowed orbits, the planet couldn't take any orbit, it had to take only special orbits. And he had a rule for determining what the orbits were, which you don't need to know. And then he said, well, what happens is where this light is coming from. If you look at this picture, this is an electron in this orbit jumping down to this orbit, and out comes light. What he said was very simple, that if the frequency of the light that comes out is just difference in energy, the amount of energy the electron has over here minus the energy it has over here. It jumps, it's as if the Earth moved from its orbit down to Mercury's orbit, which has lower energy. So the electron drops down, it emits light, and the light is just the difference in energy divided by, miraculously, St. Planck's H. It's coming into the game from a completely different direction, which was not understood as well. Really, at this stage, there were two directions in quantum mechanics. There was hot metals, what the heated things look like. There's also atomic physics. And I'm not going to tell you how, but it was Einstein who really brought the two ideas together. Okay, now things really get peculiar. This is de Broglie, who's French. He proposed in 1924 that somehow microscopic matter should behave as waves. Nobody knew what he meant. This was a bizarre, good idea. And these waves would interfere, just like water waves. It's the same picture I showed over here. It was not clear what was going on at all. Sorry. Back. Yeah. There was this big confusion, which was well expressed by this cartoon over here. Look, I'm a big picture guy. I say, let there be light. You guys figure out if it's a wave or a particle. Okay. Okay, well, let me jump now to 1925. Why 1925? All these ideas were floating around. Waves, particles, waves as particles, atoms going in special orbits, making jumps, light coming in little bundles called photons, a photo effect. All these ideas were somehow people were grasping there was some fundamental thing going on. And it was Heisenberg, who was then 24 years old. He was born in 1901. He was really trying to understand how Bohr's picture could work. Is there any theoretical ideas? You know, that you make light, like in the bulbs here, you need electrical currents. And so these are these electrons going around, the electrical currents. How would they possibly emit light? And in doing this, he discovered a basic scheme, which he didn't understand at all. It's called matrix mechanics. And it was but it's just the same year. It was two German physicists, Max Born, who's here, and Pascal Jordan here. They pointed out this is really rather simple mathematics, which I won't explain to you. And so with 1920, by 25, one had what is a solid predictive theory that with no holes in it whatsoever. Shortly after, Schrödinger, who's pictured here, so down here, he said particles are described by waves, and he wrote down an equation to describe these waves. The only thing he got wrong, he thought the particles were the waves. And as we'll see, that was not quite true. And so in hydrogen, for the hydrogen atom, which is an electron just going around a simple proton, lowest state would look like a wave like this. The higher states have more and more complicated waves. The waves were very important, but they were not the particle. They tell you what they're describing. One of the Bohr, it was Max Born, the same guy, pointed out next year. Born, incidentally, some of you may remember Olivia Newton-John. This was Olivia Newton-John's grandfather. Yes. He pointed out that there's a wave describing a particle. Oops. Thank you. No. They're good pictures, but we'll got yeah. The wave has some amplitude. You don't need to pay attention to the equation, but the wave has some amplitude. Let's say the wave is 2 feet high. You squared it. It's a 4 feet. That number gave you the probability of finding a particle. If you're an atom, the electrons sort of described by a wave like this, where the wave was big, most likely to find a particle there if you look for it. Now here, where it's very small, the probability was much smaller. At this point, he introduced the idea of probability into quantum mechanics. This is the first time. And as I said, the particle is not spread out. It's just the shape of the wave will tell you the chances of finding a particle in different places if you look. So at this point, I mean, yeah, the microscopic world turns out to be described by probability, since God is rolling dice here. Okay. Then the next step in the game was Heisenberg, the same guy. He's getting a little older here. He's 2 years older. He realized a thing called the uncertainty principle, which is that if you try to measure, for example, where a particle is, by shooting something at it, bump into it. That bump will stop it. So where you thought, you figured out where it was, what's doing after that, you don't know. And this is described by this, with the statement, you cannot determine position and speed of a microscopic particle at the same time. This, of course, has been applied to all kinds of jokes when you're stopped by a policeman who says you've been going 85 miles an hour, on this road, you say, no. Certainty principle says, if you know how fast I was going, and you can't tell where I was, or you know where I am, you can't tell how fast I was going. Yeah. Okay. Sorry. It's a new toy. It's described in this equation, uncertainty of position, uncertainty of particle momentum. This is interesting. It's bigger. That's the same number h. Again, Planck's h comes in here. Heisenberg described the situation. What we observe is not nature itself, but nature exposed to our method of question. You look at a system a certain way, you'll get a certain set of answers. Okay. Why is this? Think about measuring the microscopic world. Suppose we didn't have tools like little rulers or lasers and stuff, but suppose we wanted to measure where bowling balls were, or bowling pins are, by rolling a bowling ball at them, something comparable size. As we do that, ball will hit, it bang, you know where the ball was, but it'll knock the ball will move off. Now the thing in the microscopic world, it's not another set of tiny little tools compared to ordinary electrons. You have to use the things that the microscopic world is made of to measure the microscopic world. You intrinsically have to look your measurements with objects that have the same size and same energies as the things you're looking at. It will naturally interfere with it. Here. Okay. So if you measure the position with light, for example, if you're trying to measure the position of an electron with light, when the light shines the electron, it'll give it a kick. You could use very long wavelength light, painting with a very broad brush. That will tell you give you much information where it is. Very, very long wavelength light is low energy, according to the photon relation. But the longer the wavelength of light, the better it is, the lower energy. If you want a more accurate position, you have to use a much higher energy. This is why, for example, you can't get your chest X-rayed by shining daylight through it. You have to use X-rays, which are much finer. You see much finer detail. The problem was, again, I just make this point that when you look at the microscopic world, you intrinsically are going to interfere with it. This is an example over here. Count the black dots. It's nothing to do with physics. This is an example for psychology. It's called the Hermann grid. What is peculiar about it is this, sort of the act of measuring, you figure out the number of black dots, it interferes with what you're trying to measure. You can't quite put your finger on it. And this is Bohr and Heisenberg. What's interesting about this picture is they're off skiing in the Tyrol, and here's Bohr over here taking notes the whole time. In fact, Bohr, he was quite an athlete. He played soccer and with the goalposts. He was goalie once, and he's standing there. This is a high school doing a calculation on the goalpost. Along comes the ball. Oh yes, I should react to it. Okay. Let me come to another amazing aspect: the two-slit diffraction with light. If you shine light, light comes like waves on water through a single slit, like over here. And light through here, it goes through a slit. Then that light will spread out. Then it goes to two other slits. Slit here. It'll form a pattern. It's called a two-slit diffraction pattern. And like waves on water, you get a pattern on a screen. If the lower slit is shut, the upper one is open, you'll get a pattern like this standing up. And if they're both open, you get something with much more finer lines in it. This is Bohr in Copenhagen loved models. There's a model that he or some people built for him to illustrate this. Now, why is this important? Is that this pattern you get, this fraction pattern, if you do this with single electrons at a time, the bump, but I'll show you a movie of this, you'll get exactly the same pattern you get with light. So, bear with me for a moment. Oh. PowerPoint. Okay. This is actually done by Akira Tonomura in Japan in the late 80s. What you see here is one electron at a time is shooting in. It looks completely random. The electrons are going through two slits, just like light before. It's completely random, but if I can advance this a little bit, after a while you begin to see a pattern building up. This is impossible. Here, later time, it still looks pretty random, but now you get up to some thousands of electrons, you begin to see vaguely stripes, and finally, after 20,000 more electrons shot on the screen, you can see the same set of stripes you do with light. Now remember, this is interference of waves, looking exactly like interference of light waves, but it's only one electron at a time. So what is the relation of that electron to the wave? The wave is saying what is the probability where you could find the electron here. Electrons do sort of what they want. However, there is this guiding force somehow, this pattern, that's telling where they're more likely to be. But if you measure a single electron, you can't tell. It could be anywhere. But it's only when you get to large numbers you can begin to discern the pattern here. It's a very, very crucial experiment. And it really showed how the waves were describing the probability of where you find the particles. But the electrons are landing one dot at a time. The electrons are not the wave. Schrödinger thought that the wave was the electron. But it's not. It's telling only the probability. Here. Okay. More confusion about the role of particles and waves. We agreed to count it both as a wave and particle, tax purposes. Okay. Another really interesting idea that came into the game was the superposition of states. You can have a wave describing a particle moving this way. You can have another wave describing a particle moving this way. But you can make what is called a superposition of state that consists of both waves simultaneously. That would look kind of bumpy. If you make a measurement, sometimes you will see the particle moving this way, sometimes you'll see the particle moving that way. Different probabilities here. You describe the particle as a superposition of states. Schrödinger thought this idea was nonsense, even though he was father of wave mechanics. He invented a thought experiment to disprove it, called Schrödinger's cat. The idea is you put a cat in a sealed box. And there's a radioactive decay over here. And we know the radioactive decay is governed by quantum mechanics. Let's say a certain probability that when something decays, the particle goes up, sometimes it goes down. Schrödinger's apparatus, if the particle goes up, it triggers, if the particle goes down, nothing happens. If it goes up, it hits a string, hits a hammer, which breaks a bottle of poison over here. Poison spreads, kills the cat. So what he tried to show is that life and death of the cat depends on the simple superposition of states. We don't know the particle that comes out in the radioactive decay. There's a superposition coming out this way and coming out that way. Two mixed. And he translated it into macroscopic world. Which is disturbing, but in fact it's almost true. So one says that the cat is in the superposition of dead and alive states. It's neither dead nor alive until you actually further measure. Well, this gave rise to a lot of humor. About your cat, Mr. Schrödinger, I have both good news and bad news. The one I like the best is this one. The cat in the box. Tell Schrödinger I survived. And because the wanted poster, and this one's pretty good also. Schrödinger's dishes. They're both broken and not broken until you open the door. Yeah. Okay. Another very important thing in quantum mechanics, and this is going on in your cell phones every second, is what's called tunneling. This was invented by German physicist Friedrich Schwinn in 1926. At the same time, quantum mechanics came to its own. Normally, if you want to get to the other side of a mountain, you have to climb over the top. We all know that from the mountains here. However, in quantum mechanics, particles do something magic. Even though there's a barrier preventing you from going through, particles can actually tunnel through. It's called tunneling. But they can appear to the mountain and suddenly appear coming out the other side. In the microscopic world, this is actually very important. And that's underlies what everything goes on in your cell phone. I'll come back to that when I get to cell phone. Although here's another picture. If an electron hits a barrier, an electric field, classically the particle just bounces back. So it's here. In the quantum picture, this wave comes up to the barrier. Part of the wave actually gets reflected. This picture doesn't show it, but part of it actually can come out the other side. The amount that comes out the other side here depends on how high the barrier is. And if you think about it for a moment, this is a great idea, because if you want to control the flow of a current, particles going through, what you have to do is adjust the height of the barrier. Here, if the barrier is high, particles can't get through. If the barrier is low, particles get through easily. That's done with a simple voltage. That's the basic of the transistor, which is what your cell phones operate. Mine too. Okay. Another crucial ingredient was the electron spin. There was this wonderful German physicist of Schrödinger, and he tried to understand the properties of magnetic properties of atoms, and he said these electrons could either rotate, spin around one way, or they could spin around the other way. There are only two possibilities. Pauli, one of the great men, and Bohr said, nonsense. A few months later, George Uhlenbeck, Dutch, and Goudsmit independently proposed the idea, and it began to get a little accepted then. So this is a picture of one electron spinning one way, or spinning the other way. So it can't spin faster or faster. It just either a certain amount one way or a certain amount the other way. Oops. This should not be here. Okay. Pauli is very interesting. He proposed a thing called exclusion principle, which said that in an atom, the orbits, or special orbits, one could only put one electron in each orbit. One electron either spinning one way, one electron spinning the other way. This is the exclusion principle. Once you had particles in there, you could not put another one in the same state in the same place. That's very, very important for chemistry. Okay. So, but 19, in a sense, the quantum mechanics story is ending here. In 1925-27, things were falling into place. There are many starts that people didn't understand. Didn't mention all the ideas that were wrong. It's like non-conservation of energy. People who tried everything. They had no idea what was going on. And so these were the ingredients. Things like the uncertainty principle, the waves describe probabilities, how the light that came out from atoms could be understood by the Bohr model together with the spin. And light comes a little bundle of photons. At this stage, people felt confident they knew what was going on. They didn't really feel confident, but they thought they could plow ahead. And so at this point, people's attention turned to describing the real world, describing materials. And the first thing people realized is that particles come in two kinds. There were particles which obey the exclusion principle. There are particles that don't obey the exclusion principle, like light. You shine a light on something, you shine a second light on the same thing, it gets brighter. If you shine a light on one spot, shine the second one, doesn't chase the other one away. Whereas the other kind of particles obey the exclusion principle, like parked cars. If there's a car in a parking place, you can't put another car in. But, okay. I think since Evelyn is waving, you'll be able to skip this question here. It was a Pauli asked, how did electrons and metals obey? They found they obeyed the exclusion principle. That's an important point. I'll skip this. Okay. And on the basis of this, one learned by the early 30s why some materials were metals, some materials were insulators. It had to do with the fact that electrons in solids could have these very special states. And these special states in energy had gaps in between them here. So in a situation where you had a band, they're called bands, all the states are filled, it would be an insulator. Whereas if the partially filled on top, the next band is partially filled, it could be a metal. And if you think of having a full bottle, if you shake it, bottle, lab demonstration. If you shake the bottle, you won't, if it's completely full, you won't get any waves. If it's partially full and you shake it, it'll start to make waves. That's really the difference. What happens in metal, where we have the possibility of making waves, which correspond to transmission of currents, and in insulators, we can't make waves. They cannot conduct electricity. So this was understood. Now, the question is, let me get down to the practical issue of the cell phone. The quantum mechanics has been enormously important for industry. It's estimated that something like a third of the gross domestic product of the United States depends on quantum mechanics. And if you think of this, cell phones, television sets, cars, the average car contains, what, 3,000 chips, 10,000 chips? It's an easy number. Everything in a hospital is full of quantum mechanical things, magnetic MRIs, magnetic resonance imaging. All this depends on quantum mechanics. How did it start? What happened is Bell invented the telephone in 1876. Here's Bell making a phone call to his assistant, Mr. Watson, and the first 1892, the Labs, the telephone company, had to set up a link between New York and Chicago in 1892. Now, the problem is they discovered very quickly, though, is if you wanted to do long distance, make long distance telephones, the signal would die out right along. You need to have some sort of amplifier. The standard amplifier were vacuum tubes. Anybody remember vacuum tubes? Vacuum tubes were big, fragile, expensive, unreliable, noisy, and it was not a good solution, and it's very expensive. There was no way to have a transcontinental telephone connection, except for demonstration, with using vacuum tubes. So Bell Labs actually, in 1932, began asking the question. This is right after pieces fell in place. Could we use quantum mechanics to build a new kind of amplifier? To discover it was a transistor. And then by 1936, they started real experiments to do this. But the war came along. The war knocked industry into a different mode from 1941 to 1945. But the war had its benefits. Because one of the benefits was trying to make good radar. One had to make very pure metals. But it's technique called zone refining. And so things like very pure silicon, very pure germanium were now available. And these were what were used in the first transistors. And so original transistor was supposed to be something looking like this. It would look like this. This was done by John Bardeen and Walter Bratton. And Shockley was kind of the nominal boss. So this is the nominal propaganda picture. The guy who did the work are these two standing up here. He was just posing. Anyhow, at the 30th anniversary of the transistor in 1977, we actually baked a cake. So the cake we baked using licorice transfer wires to try to look like the original transistor. And Bardeen was very delighted with this. Anyhow, what happened here is this thing was supposed to conduct electricity through there's a layer of gold over here. Electricity was supposed to tunnel through the gold. What happened, unfortunately, is to avoid taking any chances, they washed the apparatus. They didn't wash the apparatus, so they washed the gold off. And so the thing worked. They made what was called a point contact transistor. It wasn't what they wanted. Nonetheless, the three of them got the Nobel Prize for this because well deservedly. Then, as Bardeen actually said, this accident set back transistor research by about 5 years. It was during that time people worked more to develop what's called the field effect transistor, which is what's used now. And so, at this stage, by the early 50s, the field effect transistor was developed, and the next step of the operation was to put them together. And so people began to build integrated circuits, putting more than one transistor together, the chip. And there's something called Moore's law. This is Gordon Moore over here, where the number of transistors you could put on a chip doubled roughly every 2 years. We're at the stage now where you each are carrying around something like 10 billion 10 billion transistors on a single chip. Here, I'm ending right now. Modern cell phones. This is a vacuum tube repeater. This, however, is the chip that's inside your phones over here, which contains on the order of 20 billion, what are called MOSFETs, metal oxide semiconductor field effect transistors here. And it was an amazing development. This is basically the story of how one got from the quantum mechanics very rapidly, people began to look for applications here. Of course, the standard cartoon, this is Mr. Bell with Watson here, say, now that I've invented it, I have this odd compulsion to hold it in my hand wherever I go and glance at it incessantly. This is actually in Japan. You sit down, you ride the subway, everybody's looking at the phone. It's completely upset. Well, this is sort of the end of the story. I just want to conclude by saying, how little physicists imagined they started studying the colors of metals in the late 1890s, in the 1880s, within 1 century, would unleash this tremendous technological revolution here. I think this is really a tremendous example, the best example ever, of how investment in basic science pays off, not in the short run, but in the long run. At this stage, thank you.
Thank you. That was fantastic. And we do have time for questions. I know that some of you have a bus to catch, so if we're still in the midst of questions and you need to bow, please just go ahead. But do we have questions for Gordon?
Am I correct that vacuum tubes essentially they amplify by having a few electrons come in and many electrons come out?
Yeah.
Whereas a transistor amplifies the energy of the electron. When it hits the barrier and comes out on the other side, it essentially has the energy of the barrier?
No. It's what question was basically that electrons in vacuum tubes. You repeat.
So the question was, in a vacuum tube, you have electron come in and then more come out on the other side that amplify it, whereas with the transistor, is it true that it's not number but the energy?
No. The transistor is controlling, it's like a faucet. It's controlling the amount of electrons that are going through, number of electrons that are going through.
So it's still the same.
The current. The energy.
How does that amplify? If you're sending 10 electrons in and you're allowing 1 or 2 or...
No, because suppose you had a little pipe that dribbled. That's controlling the height of the barrier. You have a big hose going through. So this little dribble is controlling, so it's controlling the faucet. If a little bit of water is coming through, faucet closes, it opens up. If it closes down, a lot of water goes down, the faucet opens up. It's controlling a valve.
But I don't see how that allows more electrons
because
you started with.
No, you're starting with the dribble, and what you have here is another source of electrons you're controlling. You have a little like a relay controlling the faucet, and just an ordinary. kitchen sink. I mean, if you have a little apparatus that can change the faucet setting, you control the flow of the water.
Is it by constricting the flow that it increases the frequency?
Again, where are you?
Right here. I'm
Okay.
trying to bridge the gap here. Is it by constricting the flow that the frequency increases or the speed?
Is it by constricting the flow? No. It has the same frequency. So this little dribble is oscillating at some frequency, and then the water comes through oscillating at a bigger frequency. Water comes through oscillating at the same frequency. There's a lot more water coming through. Okay, well, let me at this stage take more questions. Questions?
I was going to maybe expand. So the signal electrons that come in, those are what's communicating the sound or the signal of the electron, the oscillations. Those go in to control how big the gate is. This extra source, this extra pool of electrons, then can be left to flow.
Right.
So the incoming signal controls how big of a gate that they can go through.
The incoming signal controls the gate, controls this big flow. Yeah. So you start with a little signal. It's controlling the size of the gate, and this big flood is coming through. That's the amplified signal. Yeah. You didn't know it was going on 10 billion times in your phone that you're holding right now. Wonderful.
I wonder if the missing concept here is water pressure for the metaphor. Right? There's a bunch of electrons that want to go through, and the gate is keeping them from going through, and then you let them through in the amount that you want.
That's very nice. The metaphor is the water pressure that the electrons want to go through. You're trying to force them through. You're controlling it with this gate. And that's really what goes in. It works. It's in principle very simple. Very hard to make, especially if you wash the gold off by mistake.
So the double split experiment, some weird stuff going on there. And,
Isn't it?
there are a number of interpretations, and some people, I guess, go with a sort of Bohr interpretation. Then there's the many worlds interpretation. And then there's just, shut up and compute. I wonder what your thoughts on this are.
There are two attitudes of quantum mechanics. Quantum mechanics works really well. The question was, other interpretation of what's going on in these slit experiments over here. Is the world really governed by probability? Physicists say the wave functions really collapse. Such. Is this going on? There are two attitudes people have towards quantum mechanics. It really, really works. It's like driving a car. You don't have to understand how cars work to drive them. It's a great tool. And then when you start worrying, the big question is the relation of the observer to the system you want to measure. The system is described in quantum mechanics as superposition. You do a measurement, and that's the answer. But what should your brain also be part of the quantum mechanical system? And there's this artificial boundary between the measurer and the thing you're measuring. The role of that boundary, it doesn't make any sense. But there are two attitudes of quantum mechanics. One is worry about these things, and the other is shut up and calculate. and you'll find all the folks in this building shut up. They don't shut up, but they calculate.
But isn't it the case, if you imagine your brain as part of the wave function, then there is a deterministic version of mechanics that has probabilities. That
Honestly, this was beyond my pay scale. The theory I think that makes most sense in that line is something called cubism. Cubism, which is it's almost solipsism, is that quantum mechanics is trying to inform our individual experiences. I will say no more about it, but
Me?
oh, you.
Hi. So I'm sort of a radical. I've come to the conclusion that modern physics took a wrong turn when we abolished ether. And I'm wondering if...
Interesting.
Quantum physics is based upon that decision.
Well, special relativity is based on that. When light travels, it's not, when light travels in this room, what's happening is the air is shaking back and forth. When light travels through space, however, there's nothing. There was something called the ether that was shaking back and forth. Experiments showed that if there's an ether, we should be able to measure how fast we're moving with respect to the ether. Those experiments didn't work.
Well, if you're referring to the Michelson-Morley experiment,
Referring to Michelson-Morley.
there's an alternate explanation for that experiment. If the Earth and ether are moving together, the experiment assumed the ether was stationary in space. Together, there's a motion between them.
I think by...
I don't want to take up any more.
Okay, thank you. But however, all I want to say is that it's only tangentially relevant to quantum mechanics. All these questions of probability and such don't depend on that. And that's it. That is more the question of what happens in relativity. Yeah. Okay. Thank you.
Yes, you brought up Moore's law, and it is held to be true for these many years.
Yeah.
Do you see the stage at which Moore's law has reached its conclusion, that there's a finite step that we're achieving here with the doubling of...
In a way, yes. I mean, the limit is when you get down to the size of atoms. I mean,
Was about Moore's law. Are we sort of reaching the end of long that can continue, or is there going to continue forever?
yeah. I mean, things have gotten smaller and smaller. I mean, you saw the first transistor, but it's easy to make a cake that looked like the transistor. But now the transistors are almost the size of atoms, molecules. You can't go much beyond that because there's nothing smaller. But the big direction, of course, will be the development of what are called quantum computers. Which we don't have time to get into.
Maybe one last question, if there is one.
Why does when two waves overlap, why does that affect the direction?
Say it much louder.
When two waves overlap, why does that affect the direction the particle travels?
So the question was, when two waves overlap, why does that affect the direction of the particle?
No, it doesn't. If you have two waves going this way, one describing particles moving this way, one describing particles moving this way, you get a pattern. But if you try to do a measurement and ask which way is the particle moving, you get answer one way or the other. Now you can modify the waves, act with electric fields and such, change the shape of the waves, and control particles that way. But just these particles floating past each other, that doesn't change the motion.
Was the question about the double slit experiment, why they move?
Yeah.
So in the double split, when you send a single electron through, why does it?
Why is it?
Why does the electron go one way or another?
That's the wave goes through both slits. You said that an electron, its wave will travel this way, travels through both slits, and forms this interference pattern. So you have to add up the wave going this way and the wave going this way, and that's combined waves telling the electron where it's going to be, where it's going to end up. Here.
Okay, at this point, I think we should thank Professor Baym for a wonderful article.
Thank you all.